Hi all. This video is about computing QR factorizations using householder triangulations algorithms. So this algorithm is a bit numerically stable compared to the Grant-Smith orthogonalization, which was introduced in the last two lectures. The difference between these two algorithms is Grant-Smith process, as we saw earlier, is attempts to compute orthogonalization using triangular operations. But this householder triangulation algorithm is it's a different one. It's completely opposite. It applies orthogonal operations to make the matrix A into a triangulations. So by making a sequence of unitary operations on the left side of A, whereas the Gram-Smith operations make uh, multiply a sequence of upper triangular matrix on the right side of A to make the matrix A orthogonized, but householder triangulations applies a sequence of unitary matrices on the left side of A to make the matrix A into an upper triangular matrix. So this product Q is becomes uh, a unitary matrix or orthogonal matrix, and the full QR factorization of A is computed based on these operations in the householder triangulations algorithms. So this is the outline of the scheme. The Grant Smith that we were introduced in the last lecture is a triangular orthogonalizations, whereas the household algorithm which we are going to introduce now is orthogonal triangulations. So what does mean by orthogonal triangulations? So we sequentially apply unitary matrix on the left side of A, such a way that the A sequentially becomes upper triangular. It means that when we apply a matrix Q on the left side of A, such a way that we introduce zeros below the diagonal in the kth column. At the same time, we preserve all the zeros which were introduced in the previous operation from 1 to k minus 1. For example, let us illustrate with the case like we have a matrix A 5 cross 3, 5 rows, 3 columns. When we apply Q1, we introduce in the first column from row 2 to row 5, and all these entries are being changed where it is mentioned in the bold faces. And we apply Q2, we don't touch the first column, and we only in the operations only apply on the second and third columns, and we introduce zeros below the diagonal of the second column. And third matrix, we don't touch the previous operations, and we introduce zero below the diagonal of the third column. This can be introduced as sequentially for any n columns. So how do we compute this unitary matrix or orthogonal matrices? So this matrix, for example, at the kth step, can be computed by using an identity matrix and a special matrix called a householder reflector. So this householder reflector, what does mean by a householder reflector? What does it mean by? It mean by, for example, when we take the kth step, that the entries from the kth diagonal entry to the nth entry can be defined by a vector x, which is of the size m minus k plus 1. And when we apply a householder triangulations, it transform into uh, a, a vector similar to like that, where the first entries preserve all the energy of that particular vector, and all the other elements becomes zero, that is represented by a e1 vector. So this is similar. This pictorial representation would be something like that. We have a vector point x. When we make a reflector and reflect it to the other side, it is projected into E1 such a way that the first entry becomes non-zero and the rest of the entries becomes zero. So this householder is a hyperplane which is perpendicular to the vector v. The vector v can be represented by these expressions. So it means that it's an orthogonal to the space projected on the xe1. So it's hyperplane. It's similar to like kind of in a three-dimensional plane, two-dimensional space, and in four-dimensional, three-dimensional space, and so on. So in generally, a hyperplane is something like a set of points which is perpendicular to a particular non-zero vector. In this case, that non-zero vector is v here. So whenever this householder reflector is applied, the every point on one side of the hyperplane is mapped to its mirror image on the other side. So this can be mathematically expressed similar like we saw in the previous video. A projector can be formulated using a vector v in a similar fashion. So when we apply this, when we apply into a vector y, it projects into a space orthogonal to v. Similarly, householder reflector can be formulated where it not only projected onto that hyperplane, it reflects uh, onto the other side of the hyperplane, so that we can just the projector expressions I minus v star, this can be converted into a reflector by just simply multiplying the number 2. So this will be, you see the difference between the 10 point this expressions for p and this expression for f only contains additional factor 2, and projector P is of rank m-1 and the reflector is of a full rank unitary matrices. So there are many can be reflectors if in case of a complex domain, but in case of a real case there can be two reflectors based on the sign introduced here, introduced in the vector v. So if it is a plus sign or minus sign based on how the things are happening. For example, if this is a 1, if it is reflected with a plus sign, then it will be more near to the vector x. But if it is minus sign, it is more away from the vector x. So better for the numerical stability, one is better to choose for the sign which is projecting the further away, reflecting further away from the vector x. So the algorithm is very simple enough. Given in the algorithm 10.1, at every steps, iterative steps from 1 to n, we choose a corresponding vector x from that column of the k, and from that we compute vk. From that vk we compute the reflector matrix, and the reflector matrix is applied on this particular entries in the a matrix, so that when you keep on applying this operation from 1 to n, the a is transformed to the upper triangular matrices. And q is not explicitly computed, but in order to compute the q, it can be applied either algorithm 10.2 or 10.3, which is related to solving the matrix ax equal to b. So whenever we are applying the operations for the matrix a, we can apply similar operation for the b, which is been reflected in the 10.2. And similarly, qx also can be done by applying the operations qx by similarly the same operations applied for the a, so that the qx is computed at the end of the step from the reversing order 10 to 1. Similarly, when we wanted to compute the q explicitly, and we apply it on the identity matrix from E1 to EM. Similar way, either utilizing 10.2 or 10.3. So if we are applying 10.3, it would be a straightforward that we are going to use E1 to EM from left to right. But if we are using the 10.2, it will be the other way of computing q star I, then making a conjugate to get the result. So the operation count is going to be around n cube operations, which we are not going to go deep enough into how the way the flops are computed. So hopefully we'll see in the next video. Thank you.